So we've been working a little bit on graphing in previous sections, but in section 4.4 we really work on getting some more consistent rules and processes to allow us to graph those more consistently. So our first process is we can use something we call a table of values to help make a graph. And we're actually going to have a little bit more efficient methods later, but starting with a table is a good idea to kind of picture what we're doing with that graph. A set of all solutions of an equation forms the equation's graph. So again, that's how we make a graph, is by taking those solutions. A graph may include solutions that don't appear in a table, and a real world graph should only show points that make sense in that given situation. So in our first example, if we want to find the graph of the function rule, y equals 1/2 x minus 1, if we're going to do that using our table of values, this is what it's going to look like. So that table of values, again, is going to tell you for any of your x values, we need to figure out using that function rule to get your y values. Again, think in terms of functions. You have an input and you have an output after you follow that rule. And once I have my inputs and outputs, I can put those together into my graph. So as far as the values that you input into your function, usually you just want to choose maybe negative and 0 and positive just to see a few different types of numbers that could work for that. And if I plug those into my equation, so if I substitute instead of x in that function, 1/2 times -1, for example, minus 1, I get -3/2, and that's your y value. If I substitute some other numbers, so again 0, 1, and 2, or some other inputs I tried, and after inputting them into my function, I get -1, -1/2, and 0. So again, we just substitute and simplify, and that should give your y values as your outputs. Now that I have my x and y values, again, all I have to do is fit those into my graph. So if I just make a nice and neat graph with my x's and y's, it looks like -1, -3/2 would be down here, 0, -1, 1, -1/2, and 2, 0. And notice I went by, I think, half marks for all of these, so that's why if I go up 2 to get to 1, and over 2 to get to 1. So put all those points into my graph, and I can form that line with the function. When I graph a real-world function rule, we're going to choose appropriate intervals for those units. On the axes, every interval on an axis should represent the same change in value, so you don't want to go up by one amount and then change how much you're going by on the same graph. If all the data are non-negative, we want to show only the first quadrant. And again, that first quadrant looks like the upper right corner of that graph. That's where everything is positive. Again, in a lot of real-world situations, you don't have negatives, so we can just only look at that upper right portion. That's what we call the first quadrant. So looking at another one of those tables of values, we have a function rule, w equals 8g plus 700, and that's representing the total weight in pounds of a spa that contains g gallons of water. So we want a reasonable graph of that function rule, given that the capacity of the spa is 250 gallons. So again, reasonable just means we want to think of values that would work in this situation in real life. So first of all, I don't really want to plug in any negative values as my inputs. So notice I've set up my table of values. If I'm choosing inputs, don't want to start negative, but I can start with 0 gallons. 0 gallons would make sense. And notice I go up here by 100, 200, and I stop here at 250 because it's telling me that the capacity of that spa is 250 gallons. So if I went over that amount, it wouldn't really make sense for my graph. And again, as long as I'm substituting these values as my inputs into my function, I can end up with the outputs, which is what you are looking for in terms of weight in pounds that spa is going to weigh. So plug in 0, I get 700. Plug in 100, I get 1500. 200 gets me 2300, and 250 gets me 2700. And these values don't really matter so much as far as what you're going to choose. You only need to choose a few points to kind of get an idea of what your graph is going to look like. I just chose 100, 200 because those are nice and round numbers that are easy to plug in that function. So again, once I have my table of values, I can substitute these points into my graph. So 0, 700, 100, 1500, 200, that was 2300, and 250, and this was 2700. So as long as I have those points, again, if you have graph paper, it'd form a nice, neat line. Mine was a little bit out of order because the space isn't quite great, but as long as we pick, again, your interval is always going up by the same amount, so I pick intervals of 500 for the weight and 50 for the gallons. Again, that just makes sense because we go up to 250 as a max, and we saw our maximum weight was 2,700, so capping that at 3,000 would make sense. We don't have to go too far past that. So we could figure out from this the weight of the spa when it's empty, and we know that it's 700 pounds because the spa is empty when your gallons total is just 0. So when I use that input of 0, we saw that the weight was 700. That tells us the weight of just the spa itself without any water in it. In that last problem, the spa can contain any amount of water from 0 to 250. So I could use decimals like 20.4, or mixed numbers or fractions like 149 3/4 of a gallon. So we could connect those data points in the table because any point between the data points has meaning. So again, if I use 100, I found that from the table, but I could also use 50, decimals, fractions. Anything along that line would work as an answer. But the opposite of that is we could have some graphs that are composed of isolated points. So for example, the first question of the lesson we graphed graphed only points that represent printing whole numbers of photos. So if you solve that question from the very start, that is just only whole numbers. And we see those differences here, and we have terms for each type of graph. So continuous graph is going to be a graph that is unbroken. So that's a graph that I can connect all the points from your table, going to form a nice neat line. A discrete graph, though, is going to be composed of distinct isolated points. So that's when I can only graph one point at a time for the table, and I'm not able to connect those values from the table. We'll see examples of each. So in our first example, the amount of water in a wading pool in gallons depends on the amount of time t. In minutes, the wading pool has been filling, as related by this function rule w equals 3t. So again, as long as I have my table of values, I just use some non-negative numbers. So again, time can't be negative, so as long as I choose some values for the time, I can substitute those in and come up with some values for my graph. So if I put those values in, 0, 0, 1, 3, 2, 6, and 3, 9, I find that this graph should be continuous. So if I can fill that in with a line, because it makes sense to measure the amount of water in your pool anytime after it starts filling. So I have it labeled at 1, 2, and 3 minutes, but you can also imagine I can do 1 minute and 30 seconds, 1 minute and 27.4 seconds. Doesn't matter what time we're measuring, but I should still have that pool filling. So any of those points would still work in between. Compare that to our next situation where we're buying basketball tickets. So cost in dollars depends on the number of tickets that you bought. And we have this function for it. So C equals 16N. So it looks like those tickets cost $16 each. And first thing, again, if you're thinking of your table, since it's a real life situation, you can buy 0 tickets, but you can't buy negative. So might as well keep that to 0 and positive numbers for your inputs. And as long as I figure out a few outputs by using that function, I can fit those again into my graph. The only difference here is you cannot connect those points so that we know it's discrete, since we can only buy a whole number of tickets. I can only buy 1 ticket, 2 tickets, 3 tickets. Can't buy like 2.4 or like 3 1/4 tickets. So I cannot fill in this with a line, but I can graph these as discrete numbers of tickets. So far those function rules have been representing linear functions. So even though this is discrete, it's still a linear function because it forms a line. You can also graph a nonlinear function rule. When a function rule does not represent a real-world situation, we graph it as continuous. So again, if it's just an equation, then we graph it as if it's continuous. We only consider that discrete graphs if we're given a real-world situation. So if we're trying to graph that function rule y equals x cubed plus 1, again, as long as I use my table of values, I can pick some inputs that can work. And again, here I can use negative, 0, or positives, since we're not limited to a real-life situation. As long as I plug those inputs into my function, I get some outputs from that. You just want to make sure that you have those inputs and outputs together and graph those. Again, you can fill this in with a smooth curve because it is continuous. It's just an equation, not a real-life example. So this is non-linear. These points don't form a straight line, but if I fill that in with a curve that goes to the points as smoothly as possible, that would be my graph. And extending on that a little bit with 4.5, now we're working more about writing those function rules, not graphing them. So in our first question, again, we might solve that together in class. You can see how the value of one variable depends on the other. So we've been working with those relations before. Once we see any kind of pattern, we can write a rule. And we've been doing this a little bit already. Many real-world functional relationships can be represented by equations. And we can use those equations to find the solutions if we're given a real-life problem. So Some of our questions will be like this, where we're writing our we're writing our equation based on the word problem. So first example, the LA Rams had 70,000 people attend their first home game. After each game they win, they gain an average of 220 more fans. So we want to write a function rule that represents the total amount of fans in attendance after W wins. So again, depending on how many games they win, they could gain more and more fans. And if we're writing an equation for that, again, we just have to decide, what do they start with? They start with 70,000 fans at their first game. And if we're trying to think about how that total could change, we're adding 220 people every time they win. So if I multiply wins by 220, that'll give us the total that we're adding to that 70,000. So if 70,000 are at the first game, plus 220 for every win is represented by that 220W. So this is my function rule. The attendance is going to be 70,000 plus 220 for every win. In our next example, a kennel charges $15 a day to board dogs. Upon arrival, each dog must have a flea bath that costs $12. So we want to write a function rule that represents the total cost for n days, again, just kind of any number of days, that we're boarding plus that bath. So we also want to use that to figure out how much it costs to stay for 10 days. If I'm writing that as a function rule, I know it's going to look like this. So the cost is going to be 15n plus 12. We get the 15n because, again, it's $15 every day, so 15 times the number of days. So n days times 15 will give you your boarding cost. But we also have that bath that we have to pay for, so that is just a flat cost of 12. Again, we don't put the n next to the 12 because you're not taking a bath every day, not paying for that bath all the time. We're just paying $15 a day, so 15n, and the 12 is just paid once. So if I want to figure out how much a 10-day stay costs, again, all I have to do is substitute 10 in this expression. So if I substitute 10 in for n, 15 times 10 plus 12 would give us 162 total for that stay. If we try that again, but we try and figure out a 5-day stay instead of a 10-day stay, again, the only thing that changes is we're not substituting a 10 in that same equation. We substitute a 5 instead, so $15 a day times 5 days plus 12 for the bath is 87. We also see that it's not the same as just half of the cost. So even if I stay half the amount of time, it doesn't cost exactly half. And the reason for that is because either way, you're still paying both same price for that. Yeah, both the same price for that bath. So both stays pay the full price. Means that you can't just get a deal on the bath, and that doesn't cut it directly in half. So we're not paying $6, still paying that whole 12. But we can see that 87 is not half of 162 because they both pay for that bath total. So looking at that last page for some more examples. We want to write a function rule for the area of a triangle whose height is 4 more than twice the length of its base. So as soon as I see that height is 4 more than twice the length of its base, I can use a function just for this part of it. So the height is 4 more than twice the length of its base. And if we forget the triangle area formula, the area of a triangle is half of base times height. So if I just adjust that equation, if I know that the height is the same thing as 4 plus twice the base, so again, if I have an expression for the height, what I can do is I can go back into that formula I have for it. Instead of using two variables, I can substitute. So if I know this is the height, 4 plus twice the base, now I have area is 1/2 base times this expression, which is, again, is what I substituted in for h. If I use distribution, I can solve and get the area is twice the base plus the base squared. So I have a formula for that. And if I want to find out what the area is when the base is 16, all I have to do is substitute in 16 in that last expression, and I get 288. I think we'll actually stop there because I want to see if we can get that graph together for that last question.